Okay, this is the first part of our discussion about chapter 3. We already started discussing about polyphase circuit before the lockdown, but I will still discuss uh, some or review our previous discussion about this one, about chapter 3. And I'm recording now this lecture through my phone. I don't have my laptop. So, if the quality is not good, please bear with me. Analysis of a polyphase circuit. So this is chapter 3 of our course, and I will provide you with the handout of this one. I will upload it on Edmodo, and you can have the PowerPoint or the presentation or the slides, or I can give you the whole uh, handout. So let's get started. So what will be the content of this slide or this chapter? So the first, I will discuss about the objectives of chapter 3. So, what do we uh, expect to learn after this one? You should know them after this one. And some introduction to polyphase system. So, what are the advantages of polyphase? And the concept of double subscript notation. And the general two types of connection of a polyphase system. The power of a polyphase system. The phase sequence. And the three-phase system. Three-wire, four-wire balance, and unbalanced one. Then we also discuss how to measure power in a three-phase system. So first, what is our objective? What do we expect after this lecture or after this chapter? So after studying this chapter, you should be able to first understand the concept of double subscript notation. That's the first one. You need that one to continue learning about the polyphase system. The second one is you will appreciate the significance of polyphase system. You we will also try to analyze different interconnection of a three-phase system. We will focus on three-phase system and identify the phase sequence of a three-phase system. Calculate and measure the power in a three-phase system, and also we will try to investigate some unbalanced loading in a three-phase system. So first, what is a polyphase system? A polyphase system consists of two or more single-phase systems where the peak values of each does not occur at the same time. In electrical circuits 1 and chapter 1 and also chapter 2, the kind of alternating currents or voltages or that we discuss, they are known as a single phase. Now, if we try to combine them, this called single phase system, single phase voltages, we combine them to two or more phase voltages with different phases, then that system is called a polyphase system. So why do we need polyphase system? Because some loads are in polyphase system. For example, this is a two-phase hydro or hybrid servo motor. This is used for mostly for robotics applications. Um, it can also be used in some EVs and so on. Then we also have this higher number of phase. We call it six phase. It's a six phase. This one is a six phase rectifier, and this is used to supply high power, high loading. For example, the welding machines that need higher power, so they uses a higher number of phase. So in general rule, a polyphase system should be out of phase with each other. The phases should be out of phase. By how much? It depends on the number of phases. And to know that, it's just 360 degrees, one revolution divided by the number of phases. And that will be the phase angle between the phases. Except for two-phase. Two-phase is a special case. Why? Because for a two-phase system, it's not divided with the number of phase. So if we divide it with the number of phase, 360 divided by 2 will be equal to 180. But if we look at the diagram here, the phase angle between these two voltages is not 180 degrees, but it's actually 90 degrees. That's why two-phase is special case. But it's still considered a polyphase system. Why? Because the time they reach their peak values does not occur at the same time. That's the definition, very basic definition of a polyphase system. If they are out of phase of 180 degrees, that two phases that are out of phase by 180 degrees, we don't call it two phase, but we call it split phase. So it still has two phase voltages, but this time they are out of phase by 180 degrees. So we call it split phase. Two phase is different, it's special case. They are out of phase by 90 degrees. Split phase, they are out of phase by 180 degrees. Three phase, so it should be they are out of phase by 120 degrees, and so on. For higher number of phases, 6 phase, and this will be the diagram. If you look at the diagram, this one is a better application for a rectifier circuit. So what are the advantages of polyphase system? These are some advantages. The first one is the construction of polyphase machines such as motors, generators, and transformers are more simpler, lower cost, and more efficient than that of a single phase. The second one, this is the mainly most important advantage of polyphase system. It uses lesser material and it means lesser cost for transmission lines given a constant power compared to a single phase system. That's why in our transmission line system, power systems here in the Philippines, we all used a polyphase system. Specifically, we use three-phase system. And another advantage of a polyphase system is we have more voltage options because of that many voltages. We can connect them into different ways to have a different voltage options. And because it uses lesser material, it's more efficient, then the voltage regulation is also better than a single phase system. So now, let's discuss about the double subscript notation. This is our first objective. In engineering, double subscript notation is usually indicated through variable between two given points, which are represented by subscripts. And how do we identify them? So if you have here a circuit, a simple circuit here. Now, how do we symbolize or how do we name the voltage across R2? Here in double subscript notation, we don't call it V2, but we call it VAN. Why VAN? Because VAN or A and N are adjacent points to the R2 or the voltage across R2. So we call it VAN. And if we observe that node N is connected to the ground, or it means node N is our reference node, we can still omit that one. So we can just call it VA if the other node is connected to our reference node or the ground. So we can call it VA. VA is just the same as VAN. How about the voltage across R3? It should be VBN or simply BV. How about the voltage across R1? It should be VAB. And that VAB should be equal to the difference between the voltage at A and the voltage at B. Why? Because if we apply some nodal analysis, if the current is flowing through A to B, so the higher potential is at point A. So it should be A VA minus VB will be the potential difference at R1. And if we interchange them, if the direction is the opposite direction, then we can make it negative. Then this means that VAB is equal to the negative of VBA. Why? Because VBA is also equal to VB minus BA. So if we put the negative in there, it will still be equal to VAB. VA minus VB. Next, a star connected N phase system. So we can now start with the polyphase. So generally there are two types, star and the mesh. For star connected is a system in which one of each terminal of, of the individual voltage sources are connected with each other. So there's a common point. That common point is called the neutral point, or some books uses star point, which will be represented by the letter N. In figure A, that's a two-phase system. So it has two phase voltages that are out of phase by 90 degrees. It's not a split phase, it's two phase. So it's 90 degrees. So the single phase voltages are VA and VB, or VAN or VBN. So if we want to determine the voltage between the line A and line B, we call it VAB. Why? Because of the double subscript notation. And from that, if you know the concept behind a double subscript notation, you will know automatically that the value of VAB is just equal to VA minus VB, or VAN minus VBN. That's the advantage of using a double subscript notation. Next, for the three-phase system, so it's the same. It's connected at one point, the neutral point. Then there are three terminals coming out. So this is a three-wire three-phase system because there are three terminals coming out. You can also have four wires, and that the fourth wire will be the wire connected to the neutral point. So if we want to determine again the voltage across the line voltage, we call them the line voltage, VAB, VBC, VCA. These are called line voltages, while VAN, VBN, VCN, or VA, VB, VC, these are called phase voltage. And for a four-phase system, they're out of phase by 90 degrees. So it's the same. So if you observe here, the current flowing through the phase voltages, phase sources, is the same as the current flowing through the lines. So this means that the line current is just equal to the phase voltage. But the phase current, but the line voltage is not the same as the phase voltages. Why? Because VAB, we know that VAB is equal to VA minus VB. VBC is equal to VB minus VC. VCA is equal to VC minus VA. That's simple. And it's not the same for a star connected system. The only the same one are the phase currents and the phase line currents, but the phase voltage and the line voltage are not equal. So how do we relate them? So this is the relationship between them. If you try to solve the magnitude of the line to line voltage, it's equal to twice the magnitude of the phase voltage times sine of 180 divided by n. N is the number of phase. It depends on how many phases are there. If there are 3 phases, then n is equals 3. 4 phases, n equals 4. And line current is equal to the phase current. Why? Because we saw the diagram, it's just in series with the phase and the line. They're the same. The current flowing through the phase is the same as the current flowing through the line. How about for a mesh connected N phase system? So they are different with the star connected. Why? Because in star connected, there's a common point. Here in mesh connected system, there's no common point. This system creates a loop. That's why it's called a mesh. They are connected at each one, and they form a geometric loop figure. The line terminals then will be tapped on each phase terminals. So this means that the line voltages is also the same as the phase voltages. But this time, the line currents is not the same as the phase current, because if you look at that node here, the points, the corners of the triangle, so we can see that line current ILL will not be equal to I phase. Why? Because there are other branches connected to that node. And if there are other branches connected to that node, they're not equal. And we can apply KCL to solve that one. And again, we can use the double subscript notation. If that's BAB, then it's IA minus IB, IAB, and so on. This is a 4-phase, letter B, 4-phase system, and a 6-phase mesh connected system. So what will be the relationship between the phase and the line currents? So it's the same as the phase voltage and the phase line voltage in star connected system. Here it's the other way around. The IL now is not equal to the I phase, but it's equal to twice that I phase times sine 180 divided by n, while the phase voltage is equal to the line voltage. For star, it's the opposite. VL, V line or line voltage is equal to 2 times the V phase times sine 180 over n. And IL is equal to I phase. Here, it's the other way around. How about the power in a polyphase system? So the power in polyphase system is simple, because power is not dependent on the connection. Whatever the connection is, it's still equal to the formula. It's equal to the total power consumed by each phases. So the total apparent power is, you just multiply the number of phases times the apparent power for each phase, as well as the real power and the reactive power. Phase sequence. So what's a phase sequence? Phase sequence is the order in which the voltages attain their peak or maximum values. We can determine them through looking at their waveform in time domain. So for example, this waveform here. So the meaning of phase sequence is the order of who reaches the peak first. So here we can observe that V1 reaches, or the red voltage reaches the peak first. Then the next one will be the yellow one, V2, and the last one is V3. So what will be the phase sequence of this waveform? The phase sequence will be 1, the first one, 2, the yellow one, 3, the blue one. So the phase sequence is 1, 2, 3, or we can also call it RYB. Why RYB? Because RYB, red, yellow, and blue. So we will be using RYB in our discussion. The subscript will be RYB. Not I will not use 1, 2, 3, but some book use 1, 2, 3. Some also uses ABC. Some RST and so on. But I will be using RAB. They are all the same. So what if the waveform is not given? I don't know the waveform. I don't know how to draw those waveform. It's hard to draw. But we can use the phasor diagram. The phasor diagram, this is much easier to draw compared to the waveform in time domain. So how do we do that? So if we plot the phasor diagram, so this is, for example, the phasor diagram. I want to determine the phase sequence of this one. So what I do is, I get a point somewhere here, around here. Then what will I do next is to rotate my phasor diagram in that direction, in counterclockwise. So then whoever crosses that point first, and that will be our phase sequence. If we rotate that one, the red one will first cross that point. The second one will be the Y, or VY, then, or V yellow, then the last one will be the blue one. So what will be the sequence of this one? So simply, the sequence will be RYB. Example, determine the phase sequence of the three-phase system which are represented by these voltages. So first thing to do is to convert them into phasor form. So VR 200 angle 0, 200 angle 240, and 200 angle 120. Then let us draw the phasor diagram. Then we put a point somewhere here. Then we rotate it. So what will be the phase sequence? It will be red first, then blue, then yellow. So the phase sequence is RBY. So that's phase sequence. We can also determine the phase sequence using phase sequence detector. So these are devices. Simple devices, you just connect them directly and it will tell you if the sequence is a positive sequence or a negative sequence. They are all actually, usually there are two types. You have the positive and the negative one. RYB is positive, then the other one, RYB BYR, is the negative sequence. There are also other sequences. Later on, we will discuss them. But in this chapter, there are only two types. RYB is the same as YBR or BRY. That's all RYB. It's all the same sequence. It depends on where you put that point in our discussion. So these three pictures here, these are examples of uh, phase sequence detector. So why do we need phase sequence? Why do we need to know them? What's the significance? We know that there's no polarity for a AC system. There's no polarity. You can interchange the terminals. There's no positive and negative actually. But why do we need phase sequence? Phase sequence is just like the polarity of a three-phase system. If you miss the connection, if you miss them, not the right sequence, what will happen? So, phase sequence is important in operation of some polyphase transformers. If we connect in parallel some transformers and generators, AC generators, you should connect them at the same sequence. Otherwise, otherwise, uh, it may explode or it will not work. Those polyphase system. So you need to know the sequence of the first one so that if you connect the second one, you should also know the sequence. Then you connect them in parallel. Another one significance of phase sequence is the rotation of a polyphase induction motors. The rotation of polyphase induction motors depends on the phase sequence of the supply. If the sequence is negative, it will result to a reverse rotation. So this is a very critical application of phase sequence. So if you know the phase sequence, you know the direction. If you don't know, you cannot just simply connect them. Why? Because you don't know the rotation of that induction motor. It may cause harm in your application. So, so that's the introduction for polyphase system. We can now talk about three-phase system. We will be focusing about three-phase system. So the first part will be about unbalanced systems. And this unbalanced system, balance system, we will be talking about balance system first. Then after that, we talk about the unbalanced one. So what's a balance system? Balance system is where when for a three-phase balancers, when the phase voltages, the line or the magnitude of the phase voltages are equal and they are out of phase by 120 degrees. So if that is the case, then that system is a balance for the source. For the load, the impedance of each phase should also the same all phases, so that we can call it a three-phase balance load. So we will talk about the three-phase balancers, what are the characteristics, and we will also talk about the three-phase balance load and what can we do about it. So a source, if you take VRN as a reference, you can take any of them as a reference. If you want VYN as the reference, go on. If you want VBN, but usually I take VRN, it's the first one. It's always started at 0. You can also take the line voltages as the reference. When we say reference, you let that one to be equal to 0. Its phase angle will be equal to 0 because that's the reference. Not the reference node in the nodal analysis that is equal to the value 0. Here, we are talking about the phase angles or the electrical displacement. So you can make BRY, BYB, BBR as the reference. You can also make your current as your references, line current and phase currents. So if I take VRN as a reference, so this will be the values for my phase voltages in time domain. So they are out of phase by 120 degrees. So the the sequence of this one will be RYB. Then we can let the magnitude of this line phase voltages to be just equal to V phi or V phase. So VRN, the magnitude of VRN is equal to VYN because it's a balance. Then we can also let the magnitude of the line voltages to be equal to VLL or some. Later on, I will just use VL if I'm lazy. So you should know that when you see V phi, that means that's the magnitude of the phase voltage. When we see VL or VLL, then that is the magnitude of the line voltage. So what's the relationship then? Here we know VRY. So what is VRY? So if we want to solve for VRY. So from double subscript notation, you don't need to memorize the formula because you know double subscript notation. VRY is just equal to VR minus VY or VRN minus VYN and so on. So this will be the relationship between the phase voltages and the line voltages. But remember, this is not a simple algebraic subtraction. You need to subtract them uh, vectorially. So there are angles, there are phase angles here. These are vectors. So what's the relationship of line and phase voltage? The magnitude of the line voltage from our formula before is twice V phi phase voltage times sine 180 degrees divided by 3. Why 3? Because this is a three-phase system. So 180 divided by 3 is 60 degrees. And if we take the sine of 60 degrees, we have square root of 3 over 2. So if we multiply it with twice V phase, we came up with square root of 3. So square root of 3 is very important in three-phase system. You will see this one very often. Square. So where does it came from? It came from this one. It's the relationship between them. So the how about the phasor diagram? If we look at the phasor diagram of the line and the phase voltage, this will be our phasor diagram. So our reference is VRN. So obviously its phase angle should be equal to 0. So this is VRN. And we know that VRY is equal to VRN minus VYN. So this is minus VYN, which this is positive VYN here, this yellow one here. And if you want to take the negative, you just put it at the opposite direction. They have the same magnitude but opposite in direction. So if we add them, the result will be VRY. And if we try to observe here, the angle of VRY with respect to VRN is 30 degrees. That's always true. Why? Because the angle between VYN and VRN is 60. Why is it 60? Because it's 120 plus 60 is 180. So it should be 60 total. Why should it be 180? VRN negative VRN is 180 and this one is also 180. So 180 minus 120 is 60. So if we divide that with 2, 30 degrees is the angle between VRY and VRN. And if you look at each phase and line voltages, it's always 30 degrees. VYB is lagging the phase voltage, the respective phase voltage by 30 degrees. VBR and VBN. And so 30 degrees. So if we draw or if we write the value of that BRY now, this will be the values of them. It will be the magnitude of the line voltage, which is square root of 3 times V phase, and the angle is 30 degrees. Now, this is not general. Why? Because I did take VRN as my reference. So what if it's not my reference? So this will not be true. This will be incorrect. So what we do is we multiply it by 1 squared, 1 angle 30 degrees. It's not VLL. You multiply it with VR in times square root of 3 angle 30 degrees. That's the general way of solving that one. But in this example, I make VRN as my reference. But later on, if you draw the line and phase voltage phasor diagram, it should look like this. But you can rotate them whatever you want. You can make VRY as your reference, so the drawing will not be look the same as this one. It will rotate. So we can now conclude from that discussion that the phase voltages are 120 degrees apart. Why? Because they're three phase, 360 divided by 3. And also, we observe that the line voltages are also 120 degrees apart if they are a balanced system. And another one, very interesting that thing that we observe is the line voltages are actually 30 degrees ahead of their respective phase voltages. We've seen that one in our drawing, 30 degrees. Then we also know that the ratio of the magnitude of the line voltage to the phase voltage is equal to square root of 3. So that's the ratio between them, square root of 3. So that's a very important factor. How about the line currents and phase currents? So they are equal. Why? Because this is star connected or Y connected, the same. So if I apply KCL at node N at the neutral point, it should be equal to 0. Why? Because this is a balanced system. You can always do that one to check your calculation. It should always be equal to 0 for a balanced system. If it's not equal to 0, there's something wrong with your solution. So if we combine them, the voltage and the currents, so this will be our picture diagram. For a lagging power factor, so lagging power factor, the current lags the voltage by theta degrees. So here, what we see is the angle between VRN and IR is theta. Because IR is the phase current, it's the same as the line current. And VRN is the phase voltage. So the angle between them is theta. And theta will be our power factor angle. And if we try to look at the angle between the line current and the line voltage, it's actually equal to 30 degrees plus theta for a lagging power factor. For a leading power factor, this is the drawing, this is the phasor diagram. So the current is above VRN because it's a leading power factor, theta. So the angle between VRY and IR will be 30 minus theta. So why do we need this? We need to know the angle between them. Why? Because if we solve for the power in Y-connected three-phase system, we have angles here. So this is our general formula. I've given this one in the first part. So for a three-phase Y-connected system, if I want to make my formula in terms of the line voltages, and these are actually equal to V phase is equal to the magnitude of the line voltage divided by square root of 3. Or VL is equal to square root of 3 times V. And IV is just equal to IL. So if we substitute this one in the formula, we have our S will be equal to square root of 3 times the line voltage times the line current. So your formula now is square root of 3. Instead of times 3, if you use the line values, you multiply it with the square root of 3. For the real power, if we substitute it again, our formula will also become square root of 3 times the line values times cosine theta, and also the Q, or the reactive power. And note that the angle theta here, because we converted into line to line values, the angle here is not the angle between the line values. It's not 30 minus theta or 30 plus theta. But that should always be the angle of the impedance of the load, or the angle between the phase voltage and the phase current phases. Although our formula is in terms of line, theta should always be the angle between the phase values. Remember that. Next, for a meshed or delta connected balanced system, so the phase and the line voltage are equal. So VRY is equal to V1, V3, V2. So these are equal. V1 is the phase voltage. VR is also phase voltage. So these are not magnitude. These are vectors. not scalar quantities, and their magnitude should also be equal. But the phase and the line currents are different. It's the other way around. It's like what we discussed before. So it should be IR will be equal to I1 minus I2. Why? Because if you apply KCL at that point, leaving and entering that node, at node R, you will came up with these formulas. And again, the magnitude of the line current will be the phase current times the square root of t. It's just like, it's the same as the phase and the line voltage in a star connected system. But in a delta, instead of voltages, we call it, we use the currents. So if we draw the phasor diagram here, so VRY is still my reference. I make VRY as my reference here. I did make VRY as the reference instead of VRN. So if we try to observe, VRY is actually the phase voltage. It's the same as the phase voltage, V1. So there's no VRN here. So that's my reference. And this is a leading power factor theta because I1 is leading VRY. And the phase currents are I1 and negative I2. So if you add them, we came up with IR. IR is equal to I1 minus I2. And if you observe again, the angle between I1 and IR is still 30 degrees. And if we try to look at the angle between the line currents, they are also out of phase by each other by 120 degrees. So 123 degrees, 120, 120. We are, the phase and the line voltages are 120 degrees apart. So the same as the line currents and the phase currents. So from here, we can conclude that the line currents are also 120 apart. The angle between the line currents with the respective currents, phase currents, is also 30 degrees, the same as the phase and the line voltage in star connected. For a lagging power factor, the angle between the line currents and the corresponding line voltages is 30 plus theta. For lagging, it's for lagging. For leading, it's 30 degrees minus theta. And we can now also say that this is what I said before, that if you want to solve for the line values, you multiply it with the square root of 3 with the angle of negative 30. Why? Because that current is lagging the line current, the phase current is lagging the line current with 30 degrees. If you multiply it with negative 30 degrees with that phase currents, and you will have the line current. In star connected, you need to multiply it with the 30 degrees because the uh, phase voltage is leading the line voltage. Here, it's the other way around. So you can use directly this formula, or you can use I1 minus I2 later on. How about the power in delta connected system? So if we look at the power here, so it's still S equals 3V phi times I phi. That's the general formula regardless of the connection. Now, the phase voltage is the same as the line voltage. The only difference is the phase current. If we divide it with the square root of 3, with the IL, or the line current, and that's the phase current. And what will be the end result? So the end result still the same as the power in Y connected system. Again, the power is independent with the connection. So whatever the type of the connection, it's always the same formula for the power. The only difference is the formula for the line value, the formula for the phase value. But in general, the power is always the same. Later on, we'll also about talking about complex power. This is a complex power. So, complex power, I discussed this one before in chapter 2. So, if you want to solve for if you want to solve for the apparent power as a vector or as a complex, it's just equal to, you just put there times 3 because it's in 3 phase, times 3 the power at each piece. But take note here, the formula, there's a vector line up at the top of V, and IV. It means these are the vector values. They're complex numbers, not the magnitude. So there's an asterisk. It means IV, or phase current, should be the conjugate value of the actual current. So you know that, you know what is conjugate. Now another formula here, we have 3 I phase squared. I phase here is the magnitude, it's not the vector, times Z phase. Z phase here is a vector. Z phi is a vector. It's an impedance. It's not the magnitude of Z phi. It's a vector quantity. So if you want to use that one, take the magnitude of the phase current, you square it, you multiply it with the complex uh, impedance, then you multiply it by 3, then you get your apparent power. You can also divide that one, but if you divide it, make sure that the the phase impedance should also be the conjugate value. You can also use these individual formulas for P and Q, but if you want that one, then it's fine. But you can use the vector one, the complex S, because it will give you directly the value for P and Q. You just take the real component of S, you have P. If you take the imaginary component of S, you have Q. Then we talk about the loads. So we're done with the the sources. How about the loads? So the loads, there are just two types of connection here. We have the delta and the Y connection. And we already discussed how to convert from delta to Y. So if we convert from delta to Y, this is our formula. From Y to delta, this is the formula. Now, this is a balanced system. So it means that Z1 should be equal to Z2 and should be equal to Z3, or simply ZY, and also the delta 1. And we came up with the formula that if we convert the delta impedance into Y, you just divide it by 3 and you get the Y impedances. If you convert from delta to from Y to delta, then you just multiply it by 3 and you get the impedances in delta connection. That's simple. So this is a very powerful method later on in calculating some complex three-phase system. We can also convert the source. How? By using the relationship between the phase and the line voltages. So here, VR, VY, and VB, these are our phase voltages, while VRY, VYB, and VBR are the line voltages. So if we want to convert, this is the relationship. We just multiply it by negative 1 over square root of 3 times the angle negative 30 degrees. Now, let's move on with, still this is under 3 wires balance system, 3 wire 3 phase balance system. So there are different types of 3 wire balance 3 phase system. So the first one is Y. What is this Y system? Y to Y. Y to Y means your source is Y connected and your load is also Y connected. That's why it's called Y to Y. So here, if we want to solve for the line currents IR, IY, IB, the line current is the same as the phase current. It's the same as the current flowing at the impedances. And also, because this is a balanced system, VR here, the voltage at Z is also VR. Why? Because it's balanced. It's the same current that's flowing from the source side to the load side. So if we multiply it with Z, you came up with VR. So if we want to solve for IR, we just make or use Ohm's law, IR is just equal to VR over Z. And that will be the line current, and so on. But remember, if you check your answer here, if you add IR, IY, IB, it should be always equal to 0. Why? Because it's a balanced load or balanced system. So let's take an example here. In this figure, Y-connected generator delivers a power to a Y-connected load with phase impedances of 3 plus J4. First, determine the phase sequence of the source. Then the line voltages, the line currents, the total power delivered, the power consumed by the load, and the power loss. So in this example, if we try to observe, we have here an impedance at the source and also impedance at the line. And the phase voltage, VR, 680 sine 370 angle negative 90, 150, then 30. So we don't have a reference here. We just try to draw that one and we use what is given and we try to solve. So what we will do here is to convert this one into simple Y to Y system so that we can directly use our Ohm's law, or you can also use KVL if you want. So solution, so these are our sources. First, to solve for the phase sequence, we need first to convert the time domain values into phase domain. So we have here negative 90, 150, and 30. So if we try to take the phasor diagram, this is our phasor diagram. So what will be our phase sequence here? So we put a point P, we rotate it. So what voltage will cross P, point P first? It should be R, the next one will be Y, and the last one will be B. So our phase sequence should be R, Y, B. Next, so this is what we want to do in our calculation. We want to convert our original circuit into this one. Why? Because it's more simpler to solve this one. If you want to solve for IR, this is equal to VR divided by that impedance. But what is that impedance? ZT. We need to solve that first. So how do we solve that ZT? Or before we do that, how about the line voltages? So again, VRY is equal to VR minus VY. You can use this one, or you can multiply it by 1 square root of 3 angle negative 30. Or you can use this one. It's the same. So VRY will be that one. Then the other voltages will be, they are all equal because it's a balanced system. And they are out of phase by 120 degrees. So for the total impedance in the circuit, it will be equal to the series combination of the impedance of the source plus the impedance at the line and the impedance at the load. And that will be equal to 11.5 plus J 10.7. So this will be our Z total. So if you now want to find or determine our line currents, we just use Ohm's law. So IR will be equal to what? VR divided by ZT. We can now apply this one. Why? Because it's now the simplest form of Y to Y system. And we know VR. We don't use VRY because VRY is the line voltage. We need to use the phase values because we are solving for the phase current. Phase current and the line currents are the same, actually. Then for the other currents, so they are all equal. So if we try to add them, it should be approximately equal to 0. Now for the total power in the system, we can use the complex way. So I put here VR and IR because these are the vector values of the phase voltage and the phase current. You can also use BY, IY. You can also use BB, IB. It's all the same. But take note that IR, the phase current, should be the conjugate value. So our current is negative 132.94. Now we put it positive. So why? Because it's the conjugate value. Then we came up S will be equal to 32.32 plus G, 30.8 kVA. So from here, we can directly uh, identify our total power, real power. And that is 32.32 kilowatts. And also, our reactive power, 30.08 kilowatt. That is using complex power. And the Pacer diagram, if you look at the Pacer diagram, so there's no angle zero here, VBR, VRY, so VRY, VR, VR and IR. So what's the angle between VR and IR? That's 42.94. So our theta here is 42.94. So if you want to use the other formula using that Pacer diagram, P total is equal to square root of 3V line times I line times cosine theta. And our theta is 42.94. Why 42.94 in the Pacer diagram? That's the angle between the phase voltage and the phase current, not the line one. And you also came up with the same value, 32.32. And for Q, or another way is to use the other formula, I squared R times 3. Take the magnitude, you multiply it with the resistance. But take note, the resistance used here is the resistance value of the Z total, not just the load, but the total impedance, 11.5. For the load, I still use the complex at S equals 3 times IR squared times Z. So IR here is the magnitude, which is 30.61. You square that one, you multiply it with 3 plus G4. Why 3 plus G4? That is the impedance of the load. We are solving for the power of the load. So the answer here will be that one. For the power lost, it's the same formula that I used here before. I squared R lost. But what will be R lost? R lost will be the resistance at the source and the resistance at the line. So it will be 8.5 ohms. So if we substitute this one, our loss is 23.89 kilowatts. So if you observe this one, this is not a very efficient system because the loss through the lines are much higher than the power in the load. So it's not a very efficient system. And if we check it, if we add the load and the loss, it should be equal to the total power. Next, so we're done with Y to Y system. How about Y to delta system? So Y to Y, Y to delta. Let's take an example directly. So first, that figure. Identify the phase sequence of the system with the given values here. So what will be the phase sequence is RYB 0, negative 120, and negative 240. So RYB. You don't need to do that. Draw the diagram anymore. You can directly imagine the solution. Next, find the magnitude of the line-to-line voltage. So because the source is Y connected, because the source is in Y connection, given the phase voltage magnitude to be equal to 220 volts, then we can solve for the value for the line voltage is multiplied by square root of 3. And the angle will be 30, negative 90, and 50. Where does this came from? You just multiply it with square root of 3 angle 30 degrees. Then, for the phase currents, we use the phase voltages. So I1 will be equal to V1 divided by Z. Why is this? Because the voltage across the load is V1 and the current flowing through it is also I1. So we just divide them and we came up with this phase currents. Ohm's law. They are all equal and out of phase by 120 degrees. And to solve for the magnitude of the line currents, we already solved the phase current. So next is for the line currents. We can just multiply it with the square root of 3. Or we can use another formula here. If you substitute the value later here, I have here a formula, square root I phase. I phase at the load is equal to square root of 3 times the phase value voltage of the voltage at the source divided by the magnitude of the impedance, because we're talking about the magnitude. And this one is also, we know this one. If we substitute this one here, we will came up with this formula. You just divide it by z and you multiply it by 3. So this is what I use here. This formula here. So you can use that formula directly, or you can do KVL or whatever you want. You can, for the phasor diagram. So here VR is still my reference. That's my reference. Then VRY. Then the angle between VRY, the line and or the phase voltage and the line current. Phase current is 23.13. It's 53.13 minus 30. So if we want to solve for the power, here you need to use 53.13. So the power will be this one and Q will be this one. So this is without using the complex power. You can use the phasor diagram. But if you want to use the complex power, it's the same value. For a delta-delta system, in Y2 delta system, you can also make another method to solve that one. Y2 delta is you can convert the Y load or the delta load into Y load by using our transformation, then apply Y to Y. Here, it's delta delta. It's much easier than the first one, because the voltage at phase voltage at the load is the same as the phase voltage at the source. So if I want to solve for IRY here, it's just equal to the voltage here, which is VRY divided by Z, Ohm's law, directly. Then if I want to solve for the line current, then I just subtract IRY and IBR. So let's try to solve. Let's make it more difficult. Let's put an impedance at the line, ZL. So how do we solve this one? A balanced delta connected load having an impedance per phase value which is equal to 18 minus J24 ohms connected in a delta connected source. If the source is positive sequence, which is RYB, having 330 volts per phase magnitude. Taking VRY as the reference and line impedance equal to this one, calculate the phase currents of the load and the line currents. So first, it's a positive sequence, so RYB, and we take VRY as our reference. So here, I converted that delta load into a Y load. Then after converting that one into Y, that ZY is just in series with ZA. So this will be the result of the series combination. Then that value of ZY, because I converted it, we know that you just divide it by 3, then ZY is equal to that one. If the other way around, you multiply it by 3. Why? Because it's a balanced load. And now, I can also convert the voltages so that it will become Y to Y system. Using our conversion, you just multiply it with 1 square root of 3 angle negative 30. Then this will be our new circuit. It's a Y to Y system. And if it's a Y to Y2 system, you're gonna solve for the line currents. So what will be our line currents? Our line currents will be VR divided by ZL plus ZY. So that's the line current, and these are the other line currents. So we solve now the line currents. How about the phase currents? In Y to Y, the line currents is the same as the phase currents, but in the original problem, it's a delta connected system. So the phase current is not the same as the line current. So how do we solve for the phase current? We can apply KVL at that loop R, Y, R, small y to y. So if we apply KVL, this will be our formula BRY positive minus IR times ZL minus IRY times Z plus it's plus because IYY is the opposite direction as the path times ZL and it should be equal to 0. Then we already know the line values, so the only unknown here is IRY. We can solve for IRY. And we will came up with 13.2 angle 36.87. Then after that, you can use any loop if you want. You can use any path. After that, you can use KCL to solve for the other values of the phase current. So for the phase currents, if we already know the line currents are RR. Here, we already solved IRY, so we can now solve for IBR using KCL at node R. So IBR will be equal to IRY minus IRR. So the answer will be 13.2 angle 156.87 amps. So they have the same magnitude with the IRY. So our answer must be correct. And next, for the Y1, at node Y, this will be the formula IYB minus IYY minus plus, why is it plus IRY because entering IYY, entering IRY. IYB is leaving, so IYB is equal to the sum of IRY and YY. Correct. Another way to calculate the phase currents is using the fact that the line currents always lags currents. So we just multiply it by the square root of 3 angle of 30. So to do that, this one, IRR is just equal to IRY times square root of 3 angle negative 30 degrees. And still the same answer. Still the same answer. So in conclusion, we have so many ways or methods to solve polyphase system, three-phase system. You can use all our discussed techniques in circuits and you will still come up with the same answer. Now, for a delta Y system, delta source and a Y load, let's take a example. Or before we take an example, I have here a formula. So what's this formula? We have here 1 squared, 1 angle negative 30. So this is actually 1 over square root of 3 negative 30 times the phase value of the voltage. VRY divided by Z, or the line, not line, it's the phase current. You multiply it with 1 over square root of 3 angle negative 30. This is the same as what we did in the last example. So if we apply that one, it's much easier than using KVL. So a balanced delta connected source with a line voltage of 220 volts is connected to a balanced Y connected load with a phase impedance of 8 plus J6. Calculate the line currents. So VRY is our reference. We assume it's not given, so we assume RYB positive sequence. So this will be our line voltages. So what will be the line currents? Using that formula, you can have the line current. So it's easier to use that formula than applying many other methods. You just multiply it with 1 over square root of 3 angle negative 30. Okay, let's stop here. I continue this one to the next presentation. So we will be talking about the other part. So I will divide it into 2 parts. Okay, see ya.